Welcome back, everyone, to INE's CCI Data Center Nexus class. In our next section, we're going to be talking about some of the basic management techniques of NXOS. We're going to take a look at the command line of just initializing the platform, going through some of the initial configuration dialog, and then some of the necessary management protocols that we would want to enable before we get into the data center specific configurations later. Another thing that I want to mention here is what the physical topology that we're going to be using for these examples. So if you take a look at this link, this is going to be posted later with the recordings as well, as well as the slides and the diagrams that we're going to be using. But for the immediate class for while we're doing the streaming, if you go to ine.co/DC diagram, this is going to bring up a PDF of the physical topology that we're going to be using for the class. Now, this diagram here is showing the overall physical wiring of our topology, which you can see is fairly large and actually fairly confusing until we get into some of the more details later of what's going on. So again, the link is ine.co/DC diagram, and you may want to hang on to this as a reference for what's going on with the physical platforms that we're going to be using. Now, specifically in this topology, what we have is two Nexus 7010s, and each of these have the M1 and the F1 10 gig E line cards. We then also have two Nexus 5548 UPs, which are the unified port versions, which means that they can run native fiber channel as well as Ethernet. We also have two Nexus 2Ks. One of them is the 1/10 gig E version, and then one of them is the 100 meg 1 gig E version. And we'll see once we actually get into the configuration of these, there's not much functional difference between the 10 gig model versus the 1 gig model, other than, of course, the 10 gig model obviously forwards a lot faster than the 1 gig model. We then also have a bunch of routers. There's four 3825 series routers that are running regular iOS. These are going to be used kind of just as end hosts and allow us to do some comparison between the regular iOS syntax for things like routing protocols or port channeling, and then compare that to what the syntax is going on in the Nexus, NXOS. And then we also have a bunch of physical servers and virtual machines that we're going to be referencing later for physical connectivity, like we have two 10 gig E-links that are going to one of the fabric extenders here, and then various other links of connectivity into the 2Ks that is going to allow us to do the actual end host testing to look at things like doing dual home to different FEXs with virtual port channels, or doing just link aggregation like NIC teaming between the platforms. But we'll come back and talk about these specifics a little bit later. What we're really going to focus on now is just the initialization of the 5K platforms, and then of the 7K as well. So just like any other regular like iOS box, the first thing that's going to happen when you start up the platform is it's going to go through the initial configuration dialog. So it's just going to ask you a couple questions like, what is the default password that you want to use? Do you want to configure an IP address for management? That type of stuff. But one thing that is significant about this is that if we take a look at the command line here, and we look at one of the 5Ks, the first thing it asks you, do you want to enforce secure password a policy, which basically means that your password for your admin user has requirements about like uppercase, lowercase numbers, non-alphanumeric characters. Within the scope of the lab exam, I would assume that they would preset this up and just give you the login and password. But the key point here is that there is a default user automatically for NXOS, and its username is admin. So here I'm going to say, no, I don't want to enforce password security, and whatever the admin password that I want to use is here. And I'm not going to go through all the specifics of the initial configuration dialog. Most of that is pretty self-explanatory as what are the options that you can set. But the key then being is that when you connect even to the console, you are always challenged for username and password authentication. So here now the default login is admin. I'm going to put the password that I assigned in there, admin, and the password. This is going to drop me off at the CLI. Now, if we look at like the show run, you'll see a lot of the commands are similar here. Things like show interface status or show interface brief. A lot of these are going to be similar to what you would have already seen in regular iOS or Catalyst iOS. If we look at the show IP interface brief, that would show any of our layer 3 SVIs. So as you get more comfortable with the NXOS, you'll see that a lot of the syntax is very comparable to what's going on in regular iOS. So for here we see at the we have the switch name followed by the pound sign, means that we're at the exec mode, which is going to be for doing debugs, for doing show commands, different clear commands. Likewise, then if we want to make configuration changes, we're going to go to global config. We say config T. So it looks fairly similar to an iOS interface, except behind the scenes, obviously there's a different code base that's actually used to control the processes. Now we'll also see here that the interface numbering uses Ethernet followed by the module or the slot and particular module and port number, regardless of what the speed of the link is. So whether it's a 1 gig link or a 10 gig link, or in the case of like the newer M1 or M2 cards, if it's a 40 gig or 100 gig link, it's always going to be referred to as just an Ethernet interface. So to figure out what mode is it actually running in, is it running in 1 gig or 10 gig or whatever the other variations, similar to regular Catalyst iOS, we could say things like show, just show interface. This is going to show us, what is the hardware capable of. In this particular case, on the 5548, we can run these as 1 gig or 10 gig. Some of the cards only allow you to run as 10 gig, depending on the individual line card of the 7K. Okay, if we were then to look at the show run output, we'll see that there's a bunch of pre-configurations in here for queuing of things like fiber channel over Ethernet. Again, we'll talk about this when we get to the storage specific class. You'll also see here that there's going to be a control plane policy actually on the 7K. If we go to the 7K here, and we'll give it a default password here. So no, I don't want to run the initial config dialog. And let's log in as admin again, which is our default user. And then let's look at the show run output. So you'll see that from the 7K, and this depends on whether you actually went through the config dialog or not. One of the things that you may see in here is a control plane policing, or a COPP policy. Now we will talk about this in more detail when we get to security and QoS, but even with the default config, you'll see that sometimes the config is kind of polluted. It's really long and involved as to what are some of the default options. 99% of the time, you would want those control plane policing features on. But in this case, I didn't configure it because I skipped the config dialog. So the configuration is fairly empty here. Okay, next thing I want to talk about is the specific software images that we're using. Now, for those of us that are coming from a traditional iOS background, we know that there's tons of different sub-releases of iOS. There's tons of different feature sets of iOS. So we have like IP only, IP plus, Enterprise plus, Advanced Enterprise Services, and so on and so forth. In the case of NXOS, it's a little bit simpler. There's going to be one unified image for each major release, or each sub-release, I should say. And it's going to basically contain all of the features. The difference is that when we want to actually enable something like OSPF or EHRP or LACP, we simply need to turn that feature on. So if we were to look at, let's say, the 7K here, and let's give it some host names so we can tell which of these platforms we're dealing with. We'll say this is hostname N7K1-1, and we'll say this guy over here is N5K1. If we look at the show feature, this is going to show you what are the currently running processes on the device. So you can see that we could run, in this case, 4 different EIGRP processes. We have FCOE, we have endport virtualization for FCOE. even some of the basic features you would normally take for granted, like you cannot enable an SVI, an interface VLAN, until you actually turn this feature on. So when you're first starting to get into the platform, it gets a little bit confusing and sometimes frustrating why something is not working. If you don't see the syntax available, most of the time it just means that the feature is not on. So sometimes it will specifically tell you, like if you try to configure a port channel and set the mode to be active, if LACP is not on, the parser is going to generate an error, saying you need to run feature LACP in order to allow you to do this. So if you take a look at show feature, it's going to tell you what's on and what's off by default. If you also look at the show license usage, this is going to show you what are the currently licensed features on the box. So basically, what can you or can you not run? And I'm not going to get into the specifics of what are all these different packages that are available. If you look in the documentation, there's one master document that explains the licensing. What do these different features mean on the 5K? Same likewise on the 7K if we show license usage. It's going to show us like MPLS package, obviously, is for MPLS features. But some of these aren't as obvious as what they do, like what is the scalable services, or what's included in advanced LAN versus enterprise services LAN. Now, what you will see is that if you try to run a feature and you are not licensed to do so, it's going to tell you that you basically don't have the license installed for that. So, for example, if I were to go to global config here and to say that I wanted to run the fabric path feature set for the 7K, I would have to say install the feature set for fabric path. But it says I don't have a license to do that, so it's not going to allow me to turn the feature on. What you can do for the platform when you're doing your initial implementation in like your live data center environment is you can turn on the licensing grace period, which then basically gives you 120 days to run any of the particular features you want. So you can run the full implementation, then you just have to install the license key before it expires, otherwise it's going to disable the feature. So now if I were to say install the feature set fabric path, now it's going to allow me to do that. Okay, it doesn't necessarily mean that the feature is on. So if I were to say show feature set, it says that fabric path is installed, but if I were to show features, it's not going to show that fabric path is actually enabled. So there's a couple basically like housekeeping commands we need to always do when we first get into the platform in order to actually start the different processes, where it's either going to be the feature command on its own, like if we want to run OSPF, that's turning the OSPF process on behind the scenes. Some of the other ones on the 5K will be under the install feature set, like for the fabric extender or for FCOE. Syntax is a little bit different on the 5K. Most of the time, this is going to be just under the feature. Like here, we would say feature fex versus feature set fex. But most of this is pretty self-explanatory. If it gives you an error message, it means you need to turn the feature on before running it. Now, one of the advantages of having this, though, and it's similar to kind of how iOS XR works, that you install individual packages and then you have to activate them on the specific line cards. And what it helps you to avoid is essentially inter-process bugs between the different features. So for any of you that have had to do a bug scrub for, I have OSPF and I have HSRP and I have, XYZ features and I'm running them all together, you have to figure out what are the critical bugs that are basically like stop work, what are things that are less severity, and then try to pick kind of like a middle of the road release that's going to allow us to run all of these at the same time. So simply based on the fact that the processes are all off by default, it means that if I'm running OSPF as my IGP, there's no reason I need to turn the EIGRP feature set on. And it means that I would not be subject to any problems in the EIGRP code or the ISDIS code or the BGP code, whatever particular features that I'm not actually using in the implementation. But again, this can be a little bit confusing once you're first starting with the platform, because normally in regular iOS, just every feature is available. It's based on just the feature set that you have installed, like Advanced Enterprise Services versus IP only. Okay, as I mentioned, we also have the licensing grace period. This is then going to depend on which particular license file key is installed. You can see this when we look at the command line. If we were to say, look at the show license file, and then what the specific name is. This is going to show you, basically what has been purchased on this platform. One of the real key points about this, though, is that when you first get the box, and of course this is talking about practical implementation for it, one of the very first things you want to do is to do a backup of the license and then TFTP it off of the device. So if there's some sort of catastrophic failure, you need to reinstall your features. Not everything is going to work unless you actually have that licensing file available. And if we look at just a directory output, you would assume that this file is your license, but it's actually not. It's not a binary file that you can actually download here. What you need to say is to license, let's see, how do we do this? Let's actually take a look at that document that I was referring to here, which is this one here. This is the PDF version of it here, but licensing the NXOS software features. But it talks about what are the different types of licenses and what feature would you need which specific license for. But getting the license file off is not as simple as just copying it. What you need to say is to backing up an installed license. This is what I need to say. Copy the license out. So you actually need to make an archive, a tar file of it first. So if I were to say copy the from boot flash my let's say the active supervisor. Okay, so in this case, if you were to have more than one supervisor, like in a 7K platform, one is going to be active, one is going to be standby. You would want this from the active supervisor, and I want to actually not copy the file, copy the licenses first. Copy licenses, boot flash. Then this is the either the active soup or the soup1, soup local. This is actually talking about all the same thing here on this one. So I want to copy that particular license. Invalid license name .tar. That's going to be the backup. So now when you look at the dir output, you can see that just based on the file size, it's not actually the same file that was originally in there. So you want to make sure to take this as kind of a precautionary measure, because if you copy this file off, it's technically not the license. You need to do the archive of it first, and then you can TFTP it off, and then if you need to recover it later, you can go ahead and do that. Okay, the next thing that is specific to NXOS versus some of the other stuff is how the high availability works. So for those of you that have already used some of the high available modular platforms like 6500 or maybe the GSR, CRS, ASR, those type of series, one of the first things we have is the redundancy of the control plane, basically the supervisor or essentially the route processor of the device. So here, if we look at my second 7K chassis, and let me log in here, and we look at the show inventory, basically this is the individual modules that are installed, we see that there's two supervisors. They're both soup1s. Basically means that one is running as a backup of the primary. So there's certain cases where if a software process crashes or there's a problem with a virtual device context, which we'll talk about a little bit later, that we could fail over to the backup supervisor and then continue to forward without having to reprogram the control plane down into the data plane. So as Mark was talking about before, one thing that is specific to these distributed forwarding platforms is that the centralized control plane, like the supervisor, takes, let's say, your MAC address table, your OSPF routing table, your BGP routing table, and once it figures out what's the forwarding table for the MAC addresses, what's the forwarding table for layer 3, it actually has to program those down into the individual line cards. So it means that when a packet comes in, regardless of whether it's layer 2 or layer 3, it's not the supervisor that's making the decision on how to forward the traffic. It's actually the switch on chip or the ASIC that's looking at the FIB, the forwarding information base, or basically in iOS what we used to call the CEF table or the forwarding table. So the key here is that by having the backup supervisors, if one of them fails, you can continue to forward traffic, and the only thing that happens is that you eventually need to reconverge the control plane, but it doesn't necessarily affect your data plane. Now, there's really not much configuration that we need to do in order to allow this to happen. As long as you have both supervisors in there, one of them is going to be active, one of them is going to be in the standby mode. Okay, the next thing that we have is the redundancy of the power. So as we saw in some of those animations of the physical platforms, they have multiple power supplies depending on the size of the chassis. Like in this particular case with the 7010s, we have 3 power supplies that are installed, and each of those power supplies each has 2 plugs, where the idea behind this is that we would basically have 2 different power grids in the data center. So we would have grid 1 and we would have grid 2. So maybe grid 1 is run from one power company, or they technically could be the same, as long as maybe for grid 1 we have different sets of UPS batteries, we have different sets of like diesel generators that are powering grid 1 as a backup, and then for grid 2 we have separate generators. So we have multiple levels of redundancy built into the data center, even down to the power. So somewhere in the data center, these grids are going to come in. So we have like our actual power panels, whether we're doing AC or DC. Then these are going to come in to the power supply units of the actual chassis. So each of these is going to have 2 different ports. So in this case, again, we have 3 power supplies, PSUs 1 through 3. Then each of these is going to go, one of them is going to go to grid 1, one of them is going to go to grid 2, and so on and so forth. So the idea behind this is that if there's some sort of catastrophic event, and let's say that the entire grid 1 goes down, like there's a power outage and our batteries fail and our backup generators fail, well then I still have this other grid that's powering the same power supply units, so I don't have any failure in either the control plane or the data plane, and I'm able to continue to forward. Now, from a design point of view, this is a big consideration for the Nexus platform because it is very power hungry. And you can see this when you look at the particular platform and you look at the show environment power. And this is going to tell you how many different power supplies that you have currently configured and currently active. In this case, we can see in this particular chassis, there's only the first 2 that are being used right now. Then if we look at the other chassis here, let's say the same thing, show environment power. This one likewise says that I have, or actually this one has only 2 installed. So the second chassis has all 3, but the third one is not active. So this one's actually not plugged into the wall. But notice here what it says, what are the total capacity of the individual power supplies. And this is going to depend on your individual power setup. Like, are you using AC, DC, are you using 110, are you using 220? So that's going to control what's the total capacity of the PSUs. But if you notice here, one of the error messages that it's basically giving us is that the M1 card and the F1 card were denied power. Because even though I have both of these power supplies, and there's actually 4 cables that are running from the PSUs plugging into the wall, based on the redundancy mode of the power, I'm not able to actually generate enough power from the grid in order to power those individual cards. So you'll see here when you go to global config and you say power redundancy, it gives you a couple different options as to what is the specific design of how the PSUs are plugged into the different grids. So do I want to do a backup of this where I'm basically only pulling power from one of the plugs, like let's say that these are plugs A and B on each of the supplies that, again, are going to grids 1 and grids 2 respectively. So I could say use just these particular ports, don't pull power from B in order to actually power the line cards, because that's basically my redundant power. If A goes down, I want to make sure that I have that power from the B plug in backup. And that's basically what this is controlling. So do I want to have redundancy for the grid and the inputs, where basically this is going to be, I believe this one here is the most redundant of all the 4 options. And if you take a look at the command reference, you could see the specific usage guidelines for this. But essentially what I need to do here in order to even get it to power the cards is basically to take it as an aggregate of all of the power and then draw them individually. So I basically need to turn redundancy off even to get the platform to even boot the cards. Okay, and the reason why is that we're, in this particular case, we're not using 220, we're using 110. So the individual plugs that are going in from the wall, they're not drawing enough power in order to do the redundancy. But again, in a real design, you would have typically grid 1, grid 2, with separate sets of batteries, separate sets of diesel generators is kind of like a last-ditch effort. Worst case scenario backup, you're going to make sure that you still have power to your particular platforms. So here I'm going to say the redundancy mode is combined. Yes, I want to enable this. This can cause service disruptions. And eventually what we should see here, assuming that I'm logging to the console, that it's now going to start to power these cards. And this is actually why from before, when we looked at the show run output, I didn't actually see any of the interfaces appear in the running config, because the cards weren't initialized and the supervisor basically wasn't addressing them. Okay, so within the scope of the lab exam, something like this you're probably not going to have to deal with because you're assuming that the platform has proper power. But definitely within a practical design, this is something that you need to consider. You need to think about what are the aggregate of all the different cards that you're going to have, because the more fans that you have, the more crossbar here, this is the fabric cards, or basically the back plane. The more cards that you have here, these are going to be pulling power. So you can see right now we only have fabric cards 1 and 2 configured. Cards 3, 4, and 5, these are not plugged into the platform. So it basically means they're not actively pulling power right now. You can also see what's nice is that at the end of this, when we show environment power, it's going to show what the total current draw is from the PSUs, which normally you would get this from like maybe your battery backup would have like an LED screen on the front that says, what's the current load on the circuit. So it says the actual draw that we have right now is 1090, and then this is the additional power that I would have available if I had additional modules plugged in. So if we plugged another M1 line card in, plugged another F1 line card in, as long as they're going to draw less than the aggregate that we have here, they should be able to run. So you'll also see that this is going to depend based on some of the other physical characteristics of the line cards. Like if you were to use the long-range optics, so if you have your SFPs that are using the single-mode fibers that are meant for your long distances, it means that the card is going to have to pull more power in order to actually send the light signal over the line. So it is definitely part of the design. You need to think of what's the overall power budget for the platform as compared to some of the lower level, like regular routers, ISR, ISRG2. Generally, those don't pull that much. But for these larger platforms, definitely it is a consideration. How much available, basically like power bandwidth do you have in your circuits, and then how much is going to be needed for this individual platform. Okay, so we should see now that those cards are now powered. We have the M1 and the F1 cards. And if we now look at the show run, we should see that now those interfaces appear. Okay, if we take a look back at the physical diagram here, you'll see that I have a couple different color codes on the 7Ks, where the pinkish color here, this is the M1 cards. So the pink color, this is for the layer 3 switching. The blue one, this is the F1 card. So this is the layer 2 only. Now, once we get into the more specific configurations, like if we're doing fabric path, or we're doing VPC, or we're doing OTV, there is going to be a difference as to which of these links that we choose in order to run that particular feature. Okay, you'll also see that they do not have mixed compatibility. So under normal circumstances, it doesn't make sense to have an F1 link on one side and then have an M1 link on the other, because there's certain features that have incompatibilities between them. And we'll talk about the specifics of that. But out of probably all the platforms that I've worked in my career, this probably has the most hardware caveats out of all of them, what features it can and cannot run based on the individual cards. Okay, so this is a quick point to note when we're looking at the 7Ks. Anything that is E1, these are the M1 cards, the layer 3 cards. The E2s, these are going to be the F1 cards, which are the layer 2 only cards. Okay, then the next thing we have is the line card redundancy as well. Now, the line cards aren't redundant in the terms of how we have active standby cards like we do with the supervisors, or we have active standby power with the PSUs. But as I was mentioning before, there are, and since in the data center, one of our main goals is high availability, we need to make sure that the distribution of the different links is set up in such a way that if there is an individual line card failure, that it doesn't knock out the entire topology. So once we start to get into more specific technical features, things like virtual port channels, there are some issues we need to take into account, like how do we do our peer keep alive link? How do we do our peer link for doing the control plane synchronization between the different platforms in order to make sure that if there's a failure of one of the line cards, that this is not going to take out our full distribution block or possibly our full core block of the network. Because like I mentioned before, maybe we only have one M1 card and the rest of the chassis is filled with F cards. If the M card goes down, it means that it loses proxy routing for all of the F cards, and then there's going to be no redundancy built into it. So not to be like a sales pitch like Mark was saying, but generally from a minimum functionality point of view, you would want to have redundant power, you would want to have redundant supervisors, and then you would want to have your F1 and M cards in pairs. So 2 F1s, 2 M1s, 2 M2s, et cetera, to make sure that if one of them fails that you have backup when we're dealing with some of the additional redundancy designs. Okay, the next thing I want to talk about is a protocol that originally came from the SAN-OS or the MDS line, which is the Cisco Fabric Services or the CFS protocol. And this is going to be used for certain synchronizations of both the configuration and the control plane of the box. Now, one of the things that we can do with this is to configure different chassis with basic management parameters like an NTP server or the radius server's address, or a feature that's known as call home, which is like if there's a problem with the line card, I want to be able to send an email to the NOC. So with Cisco Fabric Services, one of the things that you can do is to basically do a single configuration on one of the chassis, and then it's automatically going to synchronize with the other ones, either over Cisco Fabric Services over Ethernet or Cisco Fabric Services over IP. So it can be using either a layer 2 or a layer 3 transport. Okay, we also need this to synchronize certain portions of the control plane. Now, we're going to get into more details of this later, of course, but one of the key features that Cisco Fabric Services is needed for is the virtual port channel feature, or the VPC, where VPC is like an ether channel, but it's a multi-chassis ether channel, or an MCEC, or an MEC. And what CFS is going to do for us is that if one of the physical boxes that is a member of the VPC, so one of the VPC peers, if I were to learn an ARP, request and response from one of my end hosts, I want to be able to tell the other box about that. Or if I learn their MAC address association, I want to be able to tell the other box. So through the Cisco Fabric Services over Ethernet, we have this kind of in-band yet out-of-band communication for the control plane in order for the devices to synchronize what's going on. So this is important from a configuration point of view, because if CFS is not on, there are certain features that will not work. So in general, CFS should be on, and if you want to use things like NTP synchronization between boxes, or AAA, or role-based access control, we'll talk about that later, like it's assigning passwords, privileges type stuff to the users. Normally, you would want to automatically synchronize this between the boxes with NTP or with Cisco Fabric Services. Okay, so as I mentioned, it runs over both layer 2 and over layer 3. So if you see these acronyms that are CFSOE, CFSOIP, CFSOIPv6, that's talking about the particular transport that it's using. And the particular transport that is used is going to be based on the individual application. So you don't necessarily need to memorize this. There's a command, show CFS application, that tells you, do I need Ethernet or do I need IP for this particular distribution? Now, another key point of this is, let's say, like analogous to VTP domains, where with the VLAN trunking protocol, if you have 2 switches in one domain and then 2 switches in another domain, as long as their domain names are separate, they're not going to synchronize the control plane information. So CFS is kind of similar to that, where you would configure a region, and then chassis that are in the same region would be able to synchronize. Chassis that are in different regions would not be able to synchronize. So if you have different roles in the network, then you can subdivide what are the particular the regions. So let's take a look at this on the command line. Let's look at on our first 7K. If we look at the show CFS applications, it says that we could be running NTP over CFS, but this is going to be requiring either a physical fiber channel or a physical IP interface. Now, in the case of the 7K, and we're going to get into more specifics of this in storage, 7K doesn't actually support native fiber channel interfaces. It does support FCOE, but it does not support FC. So at the 5K, like the 5548UP or the 5596UP, those do support native fiber channel interfaces. So you could go like to your fiber channel HBA, you could go to your fiber channel SAN, and you wouldn't have to run FCOE. In this case, this isn't really applicable to here, because since we don't have native fiber channel, we couldn't synchronize NTP over it. But again, originally this protocol came from the SAN-OS world, where it was used to synchronize things like zoning for SAN switching, and the advertisement of things like your worldwide port names, your worldwide node names. And we'll talk about those in more detail when we get to the storage as well. So the next thing that I want to do here is just to set up basic management connectivity between 2 of the boxes. And let's say here that we have, just from a very basic topology point of view, we have N7K1-1, and we have N5K1. And in our next section, we'll talk about why am I making the host name like this. And it's going to have to do with our virtual device context allocations that we're going to do. Okay, but in this case, we haven't done VDC, so this is talking about the full physical chassis. Basically, all the line cards, all the ports are right now allocated to just a one box. Okay, then on each of these devices, we have a management 0 interface. Okay, management 0 in the case of the 7K is a port that is on the supervisor. So this means that if you have dual supervisors, you have dual management ports. And it's used for out-of-band IP management of the box. So if you want to telnet to it, you want to SSH to it, you're normally going to want to do this over management 0 as opposed to doing it in-band, because if there's a problem with your in-band data plane, you would not want that to affect your management plane. So this is the reason why within the scope of the lab exam, they say that there are 3750s in the exam, because we want to use those to connect the management ports of the Nexus in order to allow them to run some of these features like CFSOE or CFSO IP. So essentially, these devices are in the same VLAN. The actual config of the management switch is irrelevant here. As long as they have layer 2 connectivity, that's really all that we care about. So what I'm going to do now is to go to these boxes and just assign them addresses. So this first 7K is going to get 192.168.0.71. So it's the first 7K. 5K1 is going to get 192.168.0.51. This is the first 5K. So on the 7K, this actually may be pre-configured here. Let's see. This one is. Okay, on the 5K, let's see, show run interface management 0. This one is also actually configured. So one thing you would note here about the output of the IP addressing, you don't have to use the dotted decimal format, which is kind of nice. So you can just say what's the prefix, or not the prefix, what's the address, and then its prefix length. So you don't have to go through that dotted decimal conversion to figure out what's the correct subnet for them. Okay, if we look at the show IP interface brief, normally we would see any links that are running IP. But in the case of the management interface, and let's see if this shows in global config. Let's say show run include VRF context management. So we'll see there are some minor caveats between 5K and 7K. They appear a little bit different between for the management. But by default, there is a virtual routing and forwarding instance, or a VRF, for the management 0 port. Basically, what this means is that management 0 is out of band from any of the other links. So traffic cannot pass between the management 0 and a VLAN interface or any other interface that's in the normal data plane. And this is typically what you would want, that you would have your out-of-band IP management, then maybe you have your last resort management, which is like your terminal server access, or in the case of the supervisor 1 on the 7K, we have something that's known as the Connectivity and Management Processor, or the CMP, which is basically like a built-in terminal server for the supervisor. But anyways, what this means is that basically these management links, they're not in the regular global IP routing table. I would have to say show here, show IP interface brief for VRF management. Okay, so the link is up for management 0. And I want to do the same thing on 7K1. So let's say show IP interface brief, VRF management. Okay, the link is up. I should now be able to ping 192.168.0.51, which again is the 5K's address here. And I want to be able to ping over that management segment. If I just hit enter here, it's going to tell me that I don't have a route to them, because just like in regular iOS, a virtual routing and forwarding instance is a logical separation, not a physical separation, but it is a logical separation of the control plane. So if I were to say globally, what's the route to 192.168.0.51, I don't actually have that in the routing table. Okay, I have that in the VRF management table. So this means that for any verification or any configuration that is related to the management 0 interface, you need to make sure that you're always appending what is the particular VRF, which in this case is VRF management. Okay, what's nice here about NXOS versus iOS, you'll see that a lot of these options that you configure, like accessless names or VRFs or switch profiles or VPC domains, basically anything that is a user-defined name, it will then show up in the context-sensitive help, and you're able to do tab completion. So if I say ping the address, the VRF question mark, it tells me I have VRF management. If I just type M and then tab, it's going to automatically complete that for me. Okay, but I should now be able to get connectivity between them over the management link, which I can. Okay, now if we look at the show CFS peers, this is going to tell me, do I actually know about any of the other devices over the management link running this Cisco Fabric Services protocol? Right now, the only thing that I know about is my own address, so I have not discovered the 5K yet. And the reason why is that CFS OIP is currently disabled. So what I would normally want to do, and if we say show CFS, let's say status, distribution is enabled, but not for IP. So there's certain applications like NTP or AAA that we would want to turn this on for IP. Okay, so I'm going to say in global config CFS IPv4 distribute, so that's going to turn it on. And the same thing on the 5K, CFS distribute IPv4. CFS distribute, or CFS IPv4 distribute. Okay, and let's say we'll run it over Ethernet as well. Okay, in most practical cases, you would want both of these on. So do Ethernet and IPv4 distribution. If we now look at the show CFS peers, we should see that it discovered the other device on the management link, okay, which it did. So it knows about 5K1. So this now means some of the additional administration stuff, like if I want to configure NTP, AAA, et cetera, I can configure it on one of them and then just automatically synchronize it down to the other boxes. Now, in my topology here on the management link, I also have some other devices here, and we'll get into the specifics of this later as we get more detailed into the topology. But there is an NTP server that is 192.168.0.1. So I'm going to configure the 5K basically to point at the NTP server and then distribute that through CFS, and we should see that the 7K learns the NTP server's address and then can automatically synchronize. Because typically in the data center, you're going to have just a limited number of management stations that you're using, like your NTP or your PTP, which is a more accurate version of NTP. So it's used in like high-frequency trading environments where you need to do timestamping down to the nanosecond level, literally. You would want to run the PTP, which is the Precision Time Protocol. But the logic is the same as NTP. We're just trying to get the time from some sort of server that's on the management segment there. So let's then say on the 5K that we want NTP to do distribution. Okay, so distribute is talking about CFS here. So NTP distribution is on. My NTP server is 192.168.0.1. And if we look at the clock, right now this does not show the current time. Okay, so this is whatever the default time was that the box last time it was reloaded. So we should be able to see eventually that this time is going to drift further and further towards the correct time. And actually, I may not have taken my own advice here. I didn't set the VRF. Okay, so again, remember for the management topics, if you're sending traffic over the management interface, you need to make sure to use the correct routing table, use the correct VRF. So eventually we should see when we look at the show clock that this is going to sync closer and closer towards the correct time. So we'll come back and check that. Usually it takes a little bit of time to actually synchronize, but at least we have the NTP server configured. So if we now look at the show CFS applications, we should now see that now NTP distribution is enabled, and specifically it's enabled over IP. If we show run NTP, we have NTP distribute, but we don't have the NTP server command, even though I configured it. Okay, the reason why is that when you're doing CFS, you need to do a commit afterwards to actually apply the changes and say that I'm going to send those changes out down to the rest of the devices that are connected on the management segment. So now if we show run NTP, now we can see that the server's address is listed there, and NTP commit means that I actually applied the config, and it should distribute to all the other devices. Okay, I do still need to configure the other 7K to actually listen for this. So if I say NTP distribute, and then look at the show run NTP, we can see now it automatically learns, and it's almost instantaneous because they're running over the same directly connected LAN segment, that we learn whatever the particular management protocols that we're trying to use. So if we now look at the show NTP status, it says distribution is enabled. The verification of NTP, it's not as cut and dry as it is in iOS. There's no command that just tells you the clock is synchronized. What you can say is to look at the NTP session status, I believe it is here. No, it is the show NTP peer status. So we can see that we have the address configured, and it is pulled in client mode, this status code, the equal sign. Eventually we should see that this is going to change to an asterisk, which means it's actually syncing the time with them. But eventually, if we were to look at the show clock, we would see that it's going to get closer and closer towards the correct time, and the same with the other 5K. So if we show clock, we can see now it knows it's Monday, August 27th. So it's generally just a minor configuration, but it is kind of a necessary feature of the platforms to make sure that a lot of these other control plane protocols are going to work behind the scenes. And it's specifically very, very important for VPCs, the virtual port channels that we're going to be using. So in general, you should see that CFS is on. Also, when we look at the show CFS status. Okay, for IP, it's actually sending this over IPv4 multicast. So the devices technically don't need to be directly connected. You could be routing the management 0 over a layer 3 routed network, in which case you would then need to make sure that PIM is running and that the routed management network is actually multicast aware. But in our particular application here, the devices are essentially directly connected over the management segment, so there's no problem with it. Okay, the next management protocol I want to talk about is the switch port analyzer, the encapsulated remote switch port analyzer, and the ETH analyzer features. Now, probably most of you are already pretty well familiar with this from the other Catalyst platforms, where for the span process, it's basically when we're taking traffic in from like a layer 2 or a layer 3 segment, and then we're redirecting it to some collection station, whether this is for packet analysis with like Wireshark, or maybe it's going to an IPS sensor, or maybe it's going to some other collection station. There's a number of different applications we could use it for. But the basic key is that we take traffic from a local link, and then we redirect it to another local link. So this is the local span, or the just the span feature. Now, one of the additional neat features here of NXOS is the encapsulated remote span, or ER span, where previously in most other Catalyst platforms, like the access level switches, they support the R-span feature, which essentially allows you to take, let's say we have a 7K here, well, not 7K, let's say 3750. Okay, so I have a 3750 here, and I have some segment that I'm trying to sniff. So this is where my source is located. Then I have the rest of my layer 2 core. Okay, the key being here that this is a layer 2 only network. So over then the layer 2 core, I go somehow to some other destination switch. Let's say it's another 3750. And then this is where my sniffer is located. Now, if I'm trying to get traffic from this source to redirect the packets down there, I'm going to have a problem that I have multiple layer 2 hops in the transit between them. So the source is over here, destination is down here. So the original solution for this was to take the traffic from the local source and to redirect this onto a specific dedicated R-span VLAN. Okay, so an R-span VLAN is a normal VLAN that basically has its MAC table learning rules changed, that it essentially floods the traffic everywhere because we're trying to redirect packets in a promiscuous mode to the destination. But the limitation of this feature is that it assumes that everywhere in the network that these are all layer 2 trunk links that are going from my source finally down to my destination, like the sniffer or IPS sensor or whatever we're trying to use here. Now, the Nexus version of this, which is the ER span, simplifies this process by saying, I don't really care where your sniffer is located. As long as it's somewhere in the layer 3 network, that's really all that matters. So if I have my source coming in here, and then somewhere across the rest of the data center, whether they're layer 2 attached or whether they're layer 3 attached, as long as I have basically IP reachability, I can take the traffic from the different boxes. So it comes in from the source, and I encapsulate it inside of GRE. Okay, so now I have my layer 2 frame, like my layer 2 Ethernet. It's encapsulated inside GRE. Then, of course, GRE is going to have an IP header on top. This redirects then to the destination switch. Destination switch receives the GRE frame, or GRE packet, decapsulates it, and then sends it out to whatever the destination is, like your sniffer. So essentially, the advantage of this from the data center network point of view is that you could have your packet analyzers or your services like IPS, whatever you're trying to run, in any centralized location that you want. And as long as you have basic layer 3 reachability, then there's no problem with doing the redirection of the traffic to them. Now, the configuration of the feature is fairly straightforward. You just specify what is the source of the local link that you're trying to span, what's the destination in terms of the IP address that you're trying to send the traffic to. And then one other caveat here that's a little bit different on Nexus versus some of the other platforms is that when you configure the monitor session, so say monitor session 1, The type is a span source. I'm going to say that the source is whatever, like interface E11. The destination now is an IP address. So this would be like a loopback interface on the destination switch. Then I need to make sure that the span is actually enabled. So I need to say no shutdown. Okay, there's also a couple of minor options, like we need an span ID. So if you have multiple sessions, the destination switch can keep track of which one is coming from which particular device. But now when you show monitor session 1, in this particular case, it says that the source is the physical link. In this case, it's in both directions. The destination is 1111. The span ID is 1, so this is basically like a sequence number that we're agreeing upon. I also need to say what's going to be the source address of my packets, which I'm not sure if this is going to work yet because we don't actually have routing configured. But let's say the monitor span origin address, let's say 1, 2, 3, 4, anything random. Global, I need to say. Then when we show monitor session, it says now I have an origin configured. So there's not really that many commands that go along with this, and I'm going to show some examples of this later when we actually start to get traffic into the data plane and we're trying to do redirection. But the only difference is that on the other side, you would say that the monitor session type is an span source. The source address would then be the destination IP that the tunnel was going to. So on the source side, the source is the physical link, the destination is IP. On the remote side, the source address is, the source interface, I should say, is the IP, and then the destination is the physical link. It allows you to encapsulate it over GRE. So definitely a useful feature when you're trying to do some troubleshooting in the data plane of the platform. Okay, another one that's really interesting is the built-in ETH analyzer, excuse me, the built-in ETH analyzer feature. And there's a document here that talks about the specific syntax that you would need to use for this. And I'll show a couple examples of this throughout the class as we're going through different configurations in the control plane and the data plane. But basically what this is Wireshark on the supervisor, where it has the full-blown implementation built in, because basically Nexus is just a Linux box at the end of the day. So we can say configure the local ETH analyzer to monitor traffic either in-band, like in the data plane, or on the management link. Then we could give it these command line options for the different filters that you would normally be configuring in Wireshark. So let's say, for example, I want to monitor, let's say, the ping packets over my management 0 interface. So I could say ETH analyzer local interface is management, and the display filter. And the problem here is that they don't give you context-sensitive help, so you'd have to know what the exact syntax of basically Wireshark is. And that's what this document is showing you here. So let's say that the host is, let's say the host is 192.168.0.51. And then what do I want to do with this? Do I want to send it to the console, or do I want to write it to a PCAP file? Where the PCAP file, then you can TFTP it off, or FTP it off, or SCP it off, basically to your end station that's actually running Wireshark. You can open up the file and then do packet analysis on it, like you would you in your normal data plane captures. So here, let's just say, just this option. It says this was unexpected. The display filter code looks like a valid capture filter. Let's say the source network instead. So you see that the syntax is a little bit finicky because it has to be exact. Source source net 192.168.0/00/24. Display filter. I may not be able to do that one in band, or I may not be able to do that one on the management interface. Let's actually set something up here real quick. Let's look at the topology, and let's say that between. So here we have a connection between the 5K and the 7K. So these are the two boxes that we're working on right now. If we were to go to, let's say what our link is here. Let's go to interface E2, 3, and just say no shut. And then go to the downstream switch and E1, 8, just say no shutdown. We should be able to see that they're connected on these links if we show CDP neighbors. So my 1.8 is their 2.3, which is correct based on the diagram. If I were to say, let's say like basic IP. So I want to configure an interface VLAN on the 5K. First thing we need to do then is turn the feature on. Okay, feature interface VLAN globally. Okay, then I'll create interface VLAN 1. Let's get an IP address, let's say 10.0.0.51. No shutdown. And same thing on the 7K. So feature interface VLAN. Interface VLAN 1, IP address 10.0.0.71/24, no shutdown. And I should now be able to ping 10.0.0.51. Okay, because there's no other layer 2 configuration. Just like the other Catalyst platforms, this is a layer 2 switch. So VLAN 1 is going to be the default access VLAN for the ports. We see we now just have basic IP connectivity over the links. Okay, also I'm going to turn Telnet on. So let's say feature Telnet. This is on the 7K. The 5K now should be able to Telnet in there. If we Telnet 10.0.0.71, log in as admin, whatever the password I set. Okay, we can see they have basic connectivity over TCP. So now if I were to go to the 7K and turn the ETH analyzer on, let's say for the in-band interface, so this is in the data plane, this is not on the management link. I want to say that actually the capture filter, that's what the syntax was wrong, not the display filter. Let's say the TCP port is 23. Capturing in-band. So now when I send Telnet packets, we should see that these are being captured. So we could see Telnet from 10.0.0.51 going to 10.0.0.71. Okay, by default, it's going to only allow you to capture 10 packets. You can change the number that you're capturing. If you say detail after this, it shows you the full packet dump. So if I run some command, show IP interface brief, you'll see the actual payload of the frame. So similar to what you would see in Wireshark, we see it was a layer 2 Ethernet frame. This was the source MAC. This was the destination MAC. The ether type was 0x800 because it was IPv4. Then the IPv4 header says the source and destination. Header length is 20, which is normal. We see like the DSCP bits. So it's basically the same as doing this in Wireshark, except it's just locally on the box. Okay, again, the other cool thing you can do with this then is to redirect it to a file. So let's say write it to boot flash my telnet.pcap. And then I'm going to use the same filter, which was capture filters TCP port 23. Interface in-band, capture filter, TCP port 23, and then say write. Boot flash, telnet.pcap. Okay, then if we look at the directory listing, it should have this file, telnet.pcap. So now if you were to TFTP this out or to SCP it out, transfer it off the flash, you would then be able to open this directly in Wireshark and then see what's actually inside of the payload. So we'll see as we get into more details of the specific protocols that we're going to be dealing with, like VPC, Fabric Path, OTV. It is useful to actually do this to figure out what's going on behind the scenes in some of these control plane and the data plane protocols. Because with Nexus, again, since a lot of these technologies are so new, there's not as much documentation about how it's really working. There's not really like the detailed protocol level specifics that you would see like on OSPF or BGP about things like Fabric Path or OTV or any XYZ technology that's DC specific here. And one other thing I do want to mention about this is that the capture is running on the supervisor, which means it is only capturing the equivalent of what we would think as process switch traffic in regular iOS. Now, if you know anything about how the process switch process and the Ceph process work in regular iOS, you know that if you do like a debug, let's say like debug IP packet or debug anything else, normally you're only going to see the process switch traffic because that's what's going to the general purpose CPU. And the ETH analyzer is the same type of concept here, that you're normally only monitoring the packets that are punted to the supervisor. And that's why in this case that I did telnet, because telnet is going to the CPU itself, so we would be able to capture that. Okay, there is kind of a hack that you can do on this, is that for captures of layer 3 traffic, if you were to configure an access list that is logging the packets, that is going to punt the packet to the supervisor. Because if you're going to generate a syslog for it, it needs to go to the general purpose CPU first. So it's kind of a hack on ETH Analyzer. What you can do, again, is configure the layer 3 ACL, permit the traffic that you do want to sniff, then say log at the end, then permit all other traffic so you're not actually dropping traffic. You're using it just to log the packets to the CPU. Then you would be able to capture those based on your capture filter and either export them to PCAP or look at them live directly on the command line. Because we'll see that there are debugs that we can use in Nexus, but a lot of them are just not as intuitive as some of the ones that are in iOS, simply because the iOS show commands, the iOS debug commands, these are 10, 15, 20 years old already, where a lot of this stuff in Nexus is still pretty much brand new. So just the level of detail that you get is either too much detail and you can't really sort through it, or it just doesn't give you really the useful output that you're looking for. So this feature definitely can be useful when you're trying to troubleshoot some sort of problem in the actual data plane.